Only question I have is, well, two questions actually. I know that's not available because we took one in class.
Yeah.
That one still affects the whole grade. So just a question mark about the whole thing. And then I did turn in chapter 4, so I don't know.
Maybe I just haven't fixed
Flickered
it.
off into the
Well,
sunset.
I
Paperwork does
also-
sometimes.
I was kind of slacking on your class this weekend.
I turned like all of them in all at once. You got the other 3 on there, so I just don't know if it just kind of disappeared into the void.
But did you get it back?
No, because I haven't gotten them all back yet. Because I
Okay.
literally turned them in all at the same time, and we didn't have class on Monday last week.
Yeah, I don't see it at the moment, but I'll note it to fix it.
If need be, I can redo it. Just let me know.
Yeah, probably won't be necessary. I just have to find it. All right, let's get started. So first of all, I wanted to open up an extra credit opportunity for y'all. So my colleagues in the science department wanted to do this Southern Oregon Science Professionals Lecture Series where they're inviting like local doctors from the valley to kind of talk about their experiences. And so this is open to everybody. So if you want to go, I'll offer you 5 points of extra credit on the final as an extra incentive. And so we're going to have Dr. Richardson talk about how he became an eye doctor. So he is the owner of the Rogue Family Eye Care. So again, a local person that you can talk to. And so it's going to be this Friday from 1 to 2 p.m. in HEC 112. So that's on the first floor, kind of like down the hall from Rogue Central. There's 112 over there. So if you can go, just go and let me know that you attended. Maybe, you know, write 1 or 2 sentences about what you learned, and you can get extra credit. And I think the plan is they're going to record it too. So if you can't make it at that time, there should be a recording where you can still get the 5 extra credit points. So let's. So that's 1. So extra credit for the lecture. So that will be, again, 5 points for the final. Just if you attend, submit 1 to 2 sentences of what you learned. And then, so other announcements, did y'all get an email from, it might have come from Ellen Wasserman or somebody at Columbia University, maybe Caitlin. Did you get any emails from people today? So I'll send another announcement about this, but I participated in some like research thing, and they're supposed to be surveying y'all for your experiences in the course. I think we're like the control group or something, but anyways, I was just letting you know that you should be getting like a survey link, and it is legit, and I think you're supposed to be entered into like drawings for gift cards too, so keep an eye out for your email, because I thought they were supposed to go out today. That's what they told me, that it would go out to our classes. So I'll check back on that and figure out where that went. All right, any other announcements or questions or unfinished business? All right, so then we're doing chapter 7 this week. So chapter 7, we're getting into gases. And so just a quick kind of recap. So now we're starting to get into kind of phases of matter, changes, and then our gas laws. And so just a quick recap. So we said, okay, a solid is the state of matter that has a fixed shape and volume. And then we could add energy to this. And then we add energy, so then, right, we still have our fixed volume, but now it takes the shape of the container. We can start to say that there's flow, or the fact that, right, our molecules can slide past one another. And then, of course, right, we give it even more energy, and then it turns into the gaseous state, where our molecules are further apart, and then, of course, right, we have no more fixed volume, no more fixed shape. And so we want to look at gases and all about them. And so we go into this kinetic molecular theory. So this is just kind of like, how do they move? And so the basis of that theory is that gases are obviously a phase of matter. And so again, our particles are moving randomly and very fast. And then so according to kinetic molecular theory, gas particles move in straight lines until they collide either with another molecule, maybe even in a reaction, or they might just bounce off, or it could also bounce off the wall. So it's saying it's going in a trajectory, then maybe hits our balloon, and then it would bounce off. And so the other thing that we're kind of assuming too is that these are perfectly elastic collisions. So that's kind of the other assumption. And so we are taking, again, a little bit of an oversimplification with this kinetic molecular theory. And then we're also kind of assuming no interactions. And so we're going to learn that this is not true, right? So there's interactions between our molecules, but for our purposes, we're going to say that no, they're perfectly elastic for now. And so now we can start to get into, well, what is force? And so then we can say that a molecule or gaseous atom exerts a force then when it collides with the surface or other particles. So all these collisions give rise to our pressure. And okay, well, what is pressure? So I believe this is the official physics definition for pressure. So it's just defined as the force exerted per unit area by gas molecules. So that's just going to be force over area. And so again, you can kind of think about, well, how does this work? And so the easiest thing to think about is our balloon here. And so we have to think about how our balloon even stays inflated. And so, we have to remember that the atmosphere is beating down on our balloon, with all the air collisions beating it down. Well, how come our balloon just doesn't collapse? Well, it has to have, some air inside. And so it is, pushing back on the atmosphere. So creating those collisions inside the balloon to create, that counter pressure. And so then we'll kind of also see, well, how can we change the pressure? And so, of course, the pressure could be related to the number of gas particles physically, Obviously, you know that, so you can blow more air into a balloon, It'll get bigger and bigger. It also depends on the volume, so we'll see that, We could make our container larger. That lowers the pressure. We can make our container smaller, like a piston action, and see how that changes our pressure. And then the average speed also depends on the pressure, So if it's moving faster, then there's going to be more collisions. And so, of course, speed, we want to just remember that it's related to temperature. All right, and then this is just a recap of like I was saying. So again, for this kind of theory of gases right now that we're discussing, we're assuming elastic collisions. So again, when we talk about real gases, so real gases are not perfectly elastic. And so if there was some energy exchange, then these are inelastic collisions. So again, we're assuming perfectly elastic, but obviously the real world behavior is going to deviate just a little bit. And then, okay, well, how do we measure pressure? And so we have a few common units. So we have either millimeters of mercury or torr. And so these scale the same, as in 1 ATM is 760 millimeters of mercury, or 760 torr. And then we also have ATM, so that's just atmospheres. Of course, right, our standard atmosphere should just be 1. And so now let's look at how this little manometer works for measuring our pressure. And so this also relates to why we get these certain numbers, where they came from. And so notice the setup. So we have a pool of mercury on the outside, then our vacuum glass tube in the center. And so you have to understand, well, what's driving the mercury up? Well, right, we have our air beating down on the mercury from our atmospheric pressure. And then because this is a vacuum, that's going to cause the mercury to rise up in here, again, dependent on that pressure. And so that's where we get our standard measurement, again, of height. So that would correspond to the height of our column is 760 millimeters, which is also 29.92 inches. So you see both of those numbers. And so here's a good table of just all the common measurements we'll see. So you may have to, convert between these different units, again, given these factors. So we also have pascals, so these are all equal to 1 ATM. We also have kilopascals, you might also see, so that would just be equal to 1,000 pascals. PSI, so not used so much for pressure when it comes to just talking about pressure, but you'll see PSI with the car tire pressure. So a typical car is usually around 33 or so PSI for car tire. And then we also have, so we mentioned torr, we can do inches of mercury. And then this last one here, bar, is a funky unit. So usually you see bar when you're looking at the weather report. And I'm not sure on the historical significance of bar, why is bar reported. But like I said, if you go look up the local weather report, they'll have it in bars. And so it's not quite an ATM, so just a little bit higher than 1 ATM. Any questions so far? Let's do a practice one, actually. So let's do, convert 947 torr to ATM. So just a quick refresher, right? Dimensional analysis, conversion factors, all coming back again. I see an answer in the chat, but I would check that conversion factor. So we have from this data, right, our conversion factor, so 760 torr is 1 ATM. So then we can set up our dimensional analysis, right? So we're starting with torr. I want ATM on top. So then what do we get for our answer? So that sounds about right. Yeah, so I'm seeing 1.25 then in the chat. And I can do that on the calculator real quick. So 947 divided by 760. And then, yeah, keep our 3 sig figs. So excellent, 1.25 ATM. And then, of course, right, just don't forget your units. So make sure you label units just so we all know. All right, so then there are basically 4 properties of gases that we can kind of use to characterize our gases and how much is in there and everything about it. And so, of course, one of the important properties that we just went over is pressure. And so the reason why it has the units in atmosphere here is this is kind of for our universal equation, which we'll get to. And so I'll point out in the different equations when the units matter, when they don't. But otherwise, if you're doing just pressure comparisons, and you can be in different units, volume should always be in liters typically. So that's our standard unit. And then temperature, so this one is important. So maybe put a big fat star by it. But it should always, always, always be in Kelvin. So whatever you need to do, maybe a big just wherever you need to remind yourself. So this is the biggest mistake that students make in this class, is forgetting to convert to Kelvin. And this is for every calculation. So we always need it in Kelvin. So this goes back to thermodynamic relevance. We can't have negative temperatures because then that doesn't make any sense. So we have to go from a 0 to positive scale. So always in Kelvin. And then our amount can also be characterized in moles. So we'll get to that. And moles has a little symbol of N. And so the key thing, again, with gases is that all these properties are interrelated. So if we change one, then it affects all of them. And so we'll look at a few relationships. So basically, we're going to start off with our simple gas laws to kind of look at just pairs of relationships, but then we'll see how to broaden this. And so we'll start with these kind of basic pairs. So Boyle's, Charles, and Avogadro's. And so let's look at Boyle's law. And so it started with Boyle and Hooke. And so they had these little J tubes. So J tubes are basically these little tubes that you can seal and then add different pressure to it. And so they trapped some air sample in their little tube. So it's essentially a piston. Yeah, so I'll demonstrate with our less mercury filled tube. And so, of course, they use mercury to add pressure to it. So obviously mercury is pretty dense, so that's why they chose mercury. And usually mercury is used to add gases. And so we can see that kind of in our piston relationship here. So we have starting off with 1 atm of pressure, our volume at 1 liter, with our 1 kilogram weight, and then we have a 2 kilogram weight to signify that we decreased our volume. So volume went from 1 to 0.5, and then our pressure increased. And so this is the key point. So they observed an inverse relationship, right? So if we decrease the volume, right, then our pressure increases, or vice versa. And so then we have this little chart that kind of shows this relationship. Of course, the only thing is we start plateauing out here. And what's going to account for this? This is real world data. So what happens at some level, right? Extremely high pressures, extremely tiny volume.
Reactions happen faster.
Mm.
Collisions occur.
So that is true, but right now we're just talking about, like, what if we just compress the gas, though? Because it kind of bottom.
Gas turn into a liquid.
Yeah, so right, we start reaching our physical limitations, basically. So either it's going to a liquid, maybe even we could compress it right to a solid, but at some point our molecules do take up space. So that's where, again, we get some physical limitations there.
Like hydrogen and oxygen combining eventually turns to water, right?
Well, yeah, I'm not sure how that reaction goes just like without energy. Like, I'm not sure the thermodynamics of that, but the Haber-Bosch would be like a better example of that, since forcing.
The only liquid I know that.
All right, so let's look at some, we'll do my little demo here. And so we kind of have our piston. Let me pop out. All right, so we have our piston here. And so we kind of want to repeat this experiment. And so here's our pressure gauge. This is in newtons per centimeter. So I just have it set to 1, it's about 1 ATM. And then we're at about 12 centimeters here. And so we want to see this relationship. So right here's our volume. So if I turn this, so now I'm decreasing our volume. So then what do you notice about that pressure knob? Yep, so it's going up. So right, we're seeing that. So we can compress it. And so we were at 12, so if I take it down to about 6 or so, and so there I am at about 6, and so that doubled quite nicely, so just about what we expect there. So that's kind of fun. You can play with it. It's not the most exciting thing, but. And so something else that you can play with, if you haven't seen this already. Have you guys played with this FET website before? Maybe no. So sometimes you see it in like high school, but this is fun because it has, again, the same sort of thing where we can play with our gases. So let's see, let's pick our laws here. And so we're holding nothing constant. So let's add our gas here. So you have to add kind of gases to start off with. And so again, we can see the same thing. So we have our pressure here at 10.9 ATM. Notice our temperature is here in Kelvin. And so then for this one, right, we can make our box smaller and see how, right, the pressure jumped up then. And then so now let's go back to expanding it all the way. And so right now we're back down to 7. So I can post a link to this, but this is, a fun way to kind of review. Excellent. And so like we saw with our math here, so right, they're inversely related, so that means our pressure times our volume has to be constant. So again, right, as one increases, the other decrease. Oh, sorry, I forgot to do my camera work. And so then we end up with our relationship. So this is P1 V1 equals P2 V2. And so if you're using just this formula, the units do not matter. So units for pressure, volume don't matter. So just as long as, right, the units for pressure are consistent, right? So that means it could be torr and torr, right? ATM and ATM, just as long as they are the same. So same thing, right, for volume. Typically in liters, but again, it could be milliliters and milliliters, and that would work out for this one, since we're just doing a comparative relationship. And then, so then this gets into other applications. So for example, like why diving can be dangerous. So is anybody a diver in here by any chance? Yeah, so what do they tell you about rising up to the surface? And
Like, go really slow because of the, vaccine, no, you get like air, and so if you go too fast, you'll like have blood. It expands in your blood, the gases, so if you go too fast, your blood vessels will burst.
yeah, so that's exactly it. So you hear what she said, right, that you have to rise slowly because you're basically degassing. So let's kind of think about that, right, in more detail. And so first we have to appreciate like how much pressure the ocean, puts on you right away. And so for every 10 meters of depth, we experience approximately 1 additional ATM. So that's a lot. And so right, already at 20 meters then, you're experiencing about 3 ATM of pressure. And so, okay, what's happening? So, she mentioned that you have to rise slowly. And so you often hear that, right, that you have to rise to the surface slowly. And well, why? Well, you have to think about that. And so it says, right, our pressure factor is decreasing by a factor of 3. And so if you rise too quickly, then all your gases, right, so then you have to remember, well, there's gases in your bloodstream, right, CO2 to say the least, and any other gas in your body. And so, of course, if you rise too quickly, right, then that gas will expand too quickly if you don't have time to breathe it out and exhale and, right, give your body a chance to cycle it out. Then that can, damage internal organs or, pop like blood vessels in your eyes or whatever, or anything. So, yeah, that can be an issue. And of course, right, it mentions obviously exhaling so you can get out that gas. All right, so let's try this practice problem. So as you breathe, and so now this gets a little bit into biology, right? So your diaphragm moves lower, so physically increases your lung volume. And so a woman has an initial lung volume of 2.75 liters. So it's filled with air at an atmospheric pressure of 1.02. And so, okay, now we're saying, let's just say we could expand your lung volume, right before getting any additional air. So just what is the pressure in those lungs then? So how's our problem going? So what do we do?
Multiply the pressure and volume of the first one and then multiply.
Yep.
Or solve for x basically.
Yeah, so that sounds good, right? So just start identifying, right, what's your initial conditions? So V1, P1, and then, right, this is our final V2. So we could set up our equations, so P1, V1 equals P2, V2. And so now just plugging in our variables. And so just a quick check, right? So liters, so that works out. And then we'll be solving for pressure in ATM. So P2 times 0.25. And right, so always kind of sanity check yourself too before you even plug anything in. So we were at 2.75 liters. We're increasing our volume, so I'm expecting the pressure to go down. And then let's just verify that with the math. Oops. So then do we get about 0.863 ATM? So I see some nods for that. Any questions on how to get that? And so again, right, that's telling us how our lungs function. So of course, right, if you are creating essentially a temporary vacuum as your diaphragm expands, right, then of course that's why air will go in. All right, so now we'll look at Charles's law. So looking at volume and temperature now. And so now we're saying, okay, well, they have a direct relationship. So meaning if our temperature increases and all other variables are held constant, then our volume also has to increase. So again, right, that's the key thing with these relationships we're looking at, is that everything else is being held constant, right? So pressure is constant, N is constant, so the amount. And so we're saying, well, okay, if we don't want the pressure to change, right? And now you can kind of even think about this with a balloon, right? So if you have a balloon, you heat it up, well, if it can't expand, right, it's going to just explode. So that volume has to increase, right, to keep that pressure constant. So I posted a link to the PhET simulations. And let's do that. All right, so now let's see, let's hold constant. So now we have to pick pressure, and it's going to change our volume to account for the pressure. And so let's add some heat to it. So let's just again look at our starting conditions. So we're at 300 Kelvin, 9.3 ATM. And so now let's see what happens. And so right, that was a little quick. So let's do it again. So what's happening as we're heating it? What's happening to our volume? Yeah, so it's expanding until I broke it, right? And so I always forget how you dump out. There we go. Go away. Just trying to drop our pressure a little. But then we could start again, right? So now we're already at 352 Kelvin. So again, okay, we can see that effect. So we're adding heat. Our temperature is rising. Oops, hold constant pressure again, sorry. And so if pressure is being held constant, again, right, we're seeing that volume expand. And so we could do the opposite. Actually, let's watch a fun video. Yeah, so I was going to do a baby demo of this in person, but we need more liquid nitrogen. So I don't know if I should bring it for Wednesday. All right, so let's watch if I can find.
All right, we are out in the back lot here, Fox 2, Southfield. Carl from the Imagination Station in Toledo is here. Give me some. Boom.
Yeah.
We're going to make some science, aren't we?
We're going to talk air pressure today.
Okay. Now,
right.
Explain to the folks at home what we're going to do, because I'm wearing gloves, I'm wearing goggles. You just had a blowtorch, man.
We're going to get to that in a second. Well, we're going to talk about air pressure. We're going to crush some soda cans here to just get started, okay?
Okay.
So let me show you the technique. You just kind of grab the can and you flip it
Whoa!
into the tray of water. You give it a try.
Just flip it into the tray
Just
of water.
pick it up and flip it into the tray of water.
With the
With the open side down.
Okay.
What's happening is you're sealing the top of the can,
Whoa!
and the can is very, very hot.
That made me feel powerful.
Do it again.
May I do another?
Do it again. Do it again. So the steam inside is condensing
Whoa! It happened so fast.
into water vapor, dropping the air pressure inside and crushing the can because of the atmospheric pressure outside.
Now, we have to say, don't try this at home, kids. Go
Don't.
to the Imagination Station in Toledo. Let them do
Absolutely.
it for you. You
Now-
wanna do that last one?
You know what? We're going to
save
let
it?
that one go.
Okay.
You know why?
Okay.
I've got a 55-gallon drum over here, and we are going to
Yes.
crush that the same way we did those pop cans, but we're going to do
Seriously?
it with this really big torch here, okay? So I got water inside this drum.
Okay.
I'm going to heat it up for a couple seconds here to get it really hot. Then we're going to seal it.
Uh-huh.
Then we're going to drop it on the tray of ice,
Carl,
cool it.
Do you mind if I step over there while you
No
do
way,
that?
man.
I'm
You're in here.
Way
You are-
over here. You go
you
ahead
are
with
in
it.
here.
Go ahead.
You're
I'll
in
be
here.
right back in there when you're ready for me.
All right, so get this lit here.
That's the fire. Okay.
We just want to get it really, really hot.
Okay.
We're looking for some steam to come out that hole.
All right.
All right, why don't you take this for me?
Okay.
All right. I
Are
think
we
it's
ready?
hot enough. What I'm
Hot
going to do,
enough?
I'm
Okay.
going to pop this cap on. We're
Okay.
going to seal it up. Now get over here. I need your
What do
help.
I need? This side over here?
Yeah, you stay on that side.
Okay.
With your gloves, what we're going to do, once this is tight, we're going to pick it up.
Okay.
Go ahead and pick it up, step backwards,
Okay.
and walk on over here to this tray of ice.
Okay.
Pop it on. We're going to start cooling the barrel down.
Okay.
You're going to hear two things. The ends are going to pop in,
Okay.
like drum heads. So let's go ahead and rotate it just a little bit. Try to keep it on the ice.
Whoa.
Reducing the air pressure inside
Yeah.
by condensing that water vapor. All right?
It's bending inward.
A little bit. Not quite there yet. You know what? Got a little water over there. If you want to pour that right on top, let's see if
Okay.
we can speed things up. Just go ahead and dump the whole container right on top.
Oh, there it goes. I'm hearing it. Whoa! Oh, whoa!
All right. Now that, right there, yes.
That, my friends, is the power of science.
That is air pressure, man. I love that sound. So again, we cooled the water vapor down inside. We got it to condense into a liquid. That 14.7 pounds per square inch atmospheric pressure just crushes steel 55-gallon drum. And it's still going.
I feel like I just scored a touchdown. May I?
All right, so that was pretty obviously dramatic, right? So using the big torch to really get this effect. And again, let's just kind of talk about what happened. Because, right, so they had their big drum here, then they had water vapor, right? So that was kind of the key, is they selected something that they were going to heat up and then cool back down. So hence why, right, they picked water. So they knew, okay, well, we can bring water up to the gaseous state, right, have it expand the container, take up all that space. And then obviously, right, it's exerting a lot of pressure with that high temperature. And then, of course, the key part in that little video is that they closed the system, right? So they sealed it up So then you had a limited number of N moles in there, right? So then your moles were trapped. So then they cooled down the temperature, and then, right, you saw how the volume started decreasing. And of course, right, part of that was obviously now you don't have the water vapor. So again, thinking about that balloon, your water vapor was heated up, right, pressing against it. But then once they cooled it back down, the water, well then obviously, right, it's taking up less space. It's not a gas. And so that atmospheric pressure was able to crush it. So it was fun. And so you could do the little soda cans at home too, you know, if you're safe with your little mini blowtorch. And so then we get this equation. And so direct relationship, now they have their variables kind of on top of each other. So V1 over T1 is equal V2 over T2. And again, right, highlight, star, whatever. So temperature needs to be in Kelvin. Yeah.
Is the I in that equation?
Oh, sorry, a 1.
Oh, no, I'm talking about like the VIT is constant. Like, is that an I or a?
Oh, that's a slash.
Oh, slash. Okay.
Yeah, sorry, it's supposed to be V over T is equal to a constant, which we'll get into this, like I said, in a little bit. And so again, like we were seeing with either our video or the PhET simulation, so our volume of the gas is proportional to our temperature, and again, holding other variables constant, so then we have to change the volume. And so again, right, we really saw that with the big giant flamethrower, is that our greater volume, right, spreads those collisions out over a greater surface area, so the pressure is unchanged. And then obviously, if you have less moles, or right, you change the, again, the temperature, then those collisions decrease and slow down. So then we have our Charles's law, so graphically, and then of course the only thing that kind of messes up our extrapolation is obviously things condense and become a liquid, but we can still kind of follow their general trends there. And so I feel like we got a good taste of that. So this is what I was talking about, that I would sometimes have done this in class, where I bring some liquid nitrogen in and put a balloon in liquid nitrogen, and you know, you just see how the balloon collapses. And it's just more dramatic than the ice water. But again, just pretty similar to what we saw with those videos. So again, appreciating how with obviously lowering the temperature, right, that lowers the kinetic energy, so that slows down those collisions, right, leading to less pressure, versus boiling water, right, obviously more kinetic energy, so that leads to increased collisions. All right, so let's try this practice. So we have a sample of gas has a volume of 2.8 liters at some temperature, and then when we submerge it at a T equals 0 degrees Celsius, the volume decreases to 2.54 liters. So what was the initial temperature? So let's see how it's going. So I see different answers in the chat. And so, right, we start with our equation, of course. So our V1 over T1 equals V2 over T2. And so, right, make sure that you are converting this, of course, to Kelvin. So this is going to be 273 Kelvin. And so once you have that converted, then we just can plug everything else in. So again, make sure that you plug everything in correctly, right? So this is T2, and then this is, of course, V2. So we're trying to solve for T1. V1, all right, so now we can plug everything in, so 2.08, trying to solve for X, and 273, so again, just make sure that your temperature is in Kelvin, so then 2.8 times 273, then divided by 2.54, and so we had, so we should get 297 Kelvin for our answer. And then, of course, subtract, so minus 273, and then we get our answer in Celsius. Questions on that one? Yeah.
Where did you get 280 times 273? Shouldn't it be 2.8 times 2.57?
But we gotta solve for X, right? So we just like cross multiply.
Oh, it's crossed.
Yeah, because it's 2.8 times 273 equals X times 2.57.
Okay, now that was my question.
All right. Any other questions on this math? All right, let's take our 10-minute break, so be back around 2-ish or so. And then we'll keep looking at more relationships. Thank you.
Sorry, can you show me how you did that one more time? Because I somehow did it backwards and got the answer.
I think you just like,
I literally flipped it. But then when I just tried to do
Yeah.
it your way, I got the complete wrong answers. How did you do that? I'm really confused.
you, yeah, you did, because you you just flip, you put the temperature on top instead of volume, but it should be the same thing, because you're still cross multiplying to solve.
I just did the direct math.
Yeah, but then, so then if you cross multiply, you should still get the same thing.
Because I just legitimately did like the direct math.
But even if you did the direct math, like those divided by each other, it should still give you the same thing.
And that's what I mean, like I got the answer, so does it really matter?
It probably doesn't matter too much for this one, but it'll be better to do volume on top.
I
But
know, that's what I mean, I don't, when I tried to do it that exact way, I got an answer that was like way off. So I don't understand where I disconnected in my brain and just decided to flip it.
I'm not sure either, because it's like the same setup, right, basically. You just have temperature over volume, when it should be volume over temperature. But since it's proportion, doesn't really matter.
All right, I'll just
But-
keep going. Figure it out as I go.
Can we all make it back from break? All right, so let's keep looking at our gas laws then. And so this last one is pretty, I think, makes sense, right? Self-explanatory. So again, we're holding our pressure and temperature constant. And so, while volume and moles have a direct relationship, so all this is saying is, again, if we don't want our pressure to increase, then our volume has to increase, right, to accommodate the number of moles. And then for our purposes, equal volumes of gases contain equal number of molecules. So we'll revisit this concept. And so let's look at our little simulation for a second. Let me try to get rid of some gas molecules. Oh, I don't want to hold it. Go away, go away. All right, so now we want to hold pressure constant. And so we're going to increase our number of moles. Let's see if it does it. And so, right, we're increasing moles, and then of course, right, if we want our pressure to be held constant, then it's expanding, right, our container. So that makes sense. So again, it keeps expanding so that we can hold our pressure at 13 atm. So then we get our new relationship. So we're saying, let's rewrite this so everybody can see. So we're saying, okay, well, volume over moles is equal to a constant. So therefore, we can set up our V1 over N1 is equal to V2 over N2. And so again, right, this makes sense. So our volume has to be proportionate to the number of gas molecules, again, holding everything constant. So like we saw, obviously, more gas molecules means more of them hitting at the wall. So we have to think about increasing our surface area. All right, try this problem. So we have a male athlete in our study has a lung volume of 6.15 liters during deep inhalation. And so let's say that his lung had 0.254 moles of air. So during exhalation, it goes down to 2.55. So how many moles of gas does he exhale? So watch the wording on that one. So let's see how it's going. So again, let's just start with our equation. So V1, N1, V2, N2. So we have our V1, right, V2, and then N1. But then, right, we're solving for N2, so how many moles are still in his lung? So let's do that. So 6.15 liters. All right, so then let's see what that gives us. So 2.55 times our moles divided by our initial volume. So then I have that his lungs still have 0.105 moles in them. So right, we want to say, so in the lungs. But then, okay, how much did he exhale? So then we need to subtract 0.254 minus what's remaining. And so it looks like chat had the right answer of about 0.144 moles of gas, or, 0.14. I have 9 with rounding, so somewhere around there sounds good. Does that make sense for that problem? All right, so now let's put it all together. So again, we've kind of just been obviously focusing on those 3 relationships, but really we can simplify everything with this ideal gas law. So now we have our ideal gas law, or our combined gas law. And so we'll look at a few things with that. And so let's just deconstruct this formula to start off with. So obviously P for pressure, and then this is where the units matter. So when you're using this ideal gas law, these units all matter. So what I mean by that is, okay, well now pressure has to be in ATM, right? Volume has to be in liters, N is always moles, and then R is the gas constant that corresponds with these units. And so what do I mean by that? And so what I mean by that is, if you were to just Google gas constant, let's see if I can actually find the Wikipedia page. And so the problem with the gas constant is, oh my goodness, right, it comes in all these units. So the gas constant depends on the unit. And so this is where we can find, here we are, right, ATM, liters, Kelvin, moles. So this is our gas constant back at us. So 0.082. We have ours rounded to 1, so this is the more precise answer. So that's where the constant comes into play. So right, different units, different gas constant. But that's, again, why we have to be in ATM, liters, moles, and Kelvin, so that we can use this 0.0821 for our constant. So does that make sense for that? And then the next part that we want to appreciate is, well, how do we rederive all these laws back out? And really any other relationship. And so now we can get into a little baby derivation. And so let's, again, piece this out. So we have our PV equals nRT, but right, we had just finished saying that R is a gas constant, right? So 0.0821. So that means we can rearrange this to P1, or to pressure times volume over N over T is equal to R, right? Because that's our constant. And so then we can say, well, if it's always equal to this constant, then we can have, right, P1, V1 over N1, T1 is equal to any other set of conditions. And so this is the kind of combined gas law form that I like as well. So, right, I would either commit this formula to memory or, write it down. It'll probably be provided. But, right, my point is you can derive all our other relationships from this PV equals nRT. So PV equals nRT, we can set up this relationship. And so, right, we can then just eliminate any variable that's constant.
Is this like a 2 you have up there supposed to be a 1 or a 2?
Oh, yeah, 2, sorry. And so, right, eliminating any variable that's constant, so now we can go back to Boyle's law, right? So we had this volume pressure relationship, right? P1 V1 equals P2 V2, and well, the N and the T cancel out since we were holding those constant, right, with the Boyle's law scenario. But the other thing is, well, let's say that you're changing 3 variables, right? Or even all 4 variables. So it doesn't matter because you have this equation to relate them back. And then again, right, just eliminate whatever is the same. So we'll probably see some practice of that, if not today, then hopefully Wednesday. And so this just kind of re-emphasizes that. So again, I prefer this form just for my own sanity and completion's sake, but then, okay, now we can rederive out how everything works out. So we said, okay, constant moles and temperature gives us back our Boyle's law. And then, okay, Charles's law, right, we could go back up. So N and P are constant, so cancel those out. And that gives us the V1 over T1, right, equals V2 over T2. Same thing with Avogadro's, right? Now we hold P and T constant, so boom, boom. So then you're just left with V over N. And so blah, blah, blah. So, right, we can derive our other gas laws. And then our ideal gas laws also allows us to find one of our variables if we know the other 3. And so that's kind of your other challenge is, right, do I use my ideal gas law? So are we trying to solve for one of these variables, or are we, right, changing scenarios? So going from one scenario to a second one. So that helps you kind of figure out which formula to use as well. All right, so let's practice. So calculate our volume occupied by 0.845 moles of nitrogen gas at a pressure of 1.37 atm and 315 Kelvin. So let me know what you got. So of course, right, we can kind of see the setup is a little different. So we're just given moles, ATM, Kelvin. We're trying to figure out volume. So that's hinting right towards our ideal gas law equation of PV equals nRT. And then everything was already given in the appropriate units, so you didn't have to convert. So now we just have to rearrange a little bit. So nRT over P equals our volume. So you guys can yell answers at me. Times. So 15.95, so chat's saying about the same, so let me just plug that in as well. So we have 3 sig figs for our answer. So yeah, 15.95, so then we should round that to 16, right, for sig figs. Excellent. Questions on that problem? Relatively straightforward, hopefully. All right, so now we're starting to get into our STP conditions and going back to all gases occupy the same amount. And, okay, so again, because our volume of our gas varies a lot with pressure and temperature, chemists wanted to talk about a set of conditions to kind of report. And so these STP conditions are just kind of used as standard conditions. And so STP is defined as 1 ATM, 0 degrees Celsius, and 1 mole. And then this is really the key point here, is that your standard volume at STP is 22.4 liters. So, right, so we're saying any mole of substance at STP is 22.4 liters. So this will help you. So again, I'll rewrite this. So 1 mole, so again at STP, so 1 mole of gas, 22.4 liters. And again, this applies for every gas, so the identity does not matter. So in the real world, there's some fluctuation, but this is our conversion for this class. And so you could plug it in as well. So that's all that's done here. I won't redo it to belabor the point, but you can just appreciate, and you can plug it in on your own if you don't believe it. But right, obviously plugging in the appropriate variables for STP of 1 and 0 for our temperature, and 1 mole gives us that 22.4 liters back out. And right, so like I mentioned, again, 1 mole of every gas at STP is 22.4 liters. We can also add to that, right, that 1 mole is 6.022 times 10 to the 23rd molecules. So all of these little relationship tricks are useful. And then, so they will have different densities, so keep that in mind, right? So obviously, xenon is physically larger than helium, so the only difference is going to be in their density. But again, the volume is the same. So going back, right, they have different masses, density will be different, volume's the same. And then, so then we want to get into these other laws, or really just kind of relationships. And so the next thing that this is saying is, again, right, we're going off our assumptions that the particles have negligible size and do not interact. And so then that means, so if the identity of the gases doesn't matter, then we can just say that the total pressure of a gas mixture is the sum of our partial pressures. And again, right, this goes back to, so average kinetic energy is the same, so related back to temperature. So our total pressure of our collisions is the same. So then we have what's called our partial pressure. So this would just be the pressure of a single gas in a mixture. And so we can calculate our partial pressure either by knowing the fraction of the mixture it composes and then knowing the total pressure, or knowing the number of moles of a gas in a given volume. And then of course you can use your gas laws to get the pressure back out if you know the moles. And so again, right, gases are behaving independently. And so we can just add up our total pressures. And again, the derivation kind of comes from here, that it's dependent on your molar amount, right? So again, identity of the gas doesn't matter, hence why we can just add it. And so then we could calculate our mole fraction. And so this would be related to, again, their partial pressure over their total pressure, and that is the same as their mole fraction. So then that is related to what percentage of the mole they have over the total. And let's see some examples, because it'll make more sense once we see some numbers in there. And so we can think about air. So of course, right, we have mentioned that air is a homogeneous mixture. And so nitrogen has a 78% composition of air. So we want to find its partial pressure. And so we can just multiply in this case. So we know our atmosphere is 1 atm, so 1 times 0.78 for, again, the composition. And we have 0.78 atm. And then all the other parts would be additive. So, right, our atmosphere is 21% oxygen. So there's our 0.21 atm, and then, right, about 1% argon, and obviously other trace gases. So again, right, all additive to give you your total pressure. Let's see. Still have time. So then we start to get into, again, phase changes. So we've kind of been harping on this idea, right, that it's just energy that separates them, right? So we either heat them to go from solid to liquid to gas, or of course, right, we can cool them, and that results in a state change. So we've kind of gotten a small taste in that in lab as well. And so, of course, right, phase changes can be induced by generally heating, cooling, or perhaps even, right, changing the pressure. And so now this gets into, well, you know, how are things held together? And so now we have to kind of talk about, right, how our gases break our kinetic molecular theory. And so that's the first thing is, well, there really are intermolecular forces, right? So they do have some sort of interaction, these molecules. Again, right, in the gas phase, we assume that they're far enough apart that they're negligible. But once they start getting closer and closer together, right, well, that's going to have some sort of effect on them condensing. So, okay, well, let's start looking at this then. And so, again, this is something that we've been stating, but we'll state it again. So all attractive forces, right, are electrostatic. So meaning we have to have something that's positive and something that's negative, right? So opposites attract, so that's still our concept. And then the strength of these attractions determines its state, right? And so again, we've gotten a small hint of that. So we've said, well, those ionic compounds, they tend to have really strong attractive forces, so they tend to be solids. While we said, right, the covalent compounds tend to be weaker and, right, be liquids, even, or gases, or, you know, pretty low boiling. So most covalent compounds I would consider are low boiling. And so, of course, right, at room temperature, if we have moderate to strong attractive forces, then we have solids or liquids. And then, obviously, the stronger the attractive forces, the higher the boiling point and melting point will be. So again, we'll kind of start to understand that correlation. And so these attractive forces vary in strength. So we'll talk about these various types of forces. And then, right, obviously the stronger the attractive forces between the particles, the more they resist moving. So again, going back to solid state of matter. And then like we've mentioned before, so no material completely lacks particle motion. So, right, to completely lack particle motion would be at absolute zero, or you have complete absence of motion. So, right, everything's still vibrating, even as a solid. All right, so again, like we've been saying, so the stronger the attractions between the atoms or molecules, the more energy it takes to separate them. And so boiling a liquid means that we're adding enough energy to overcome the attractions between the particles. So again, we're thinking about breaking those intermolecular forces. So between the molecules, right? So it's saying that we're not breaking covalent bonds. So AKA those intramolecular forces, right? We're not breaking bonds, we're just breaking the between the bonds. Or, sorry, between the molecules, just to emphasize that. And so again, the higher the normal boiling point of our liquid, then that's indicating stronger intermolecular forces.
Catalog of chemical terminology.
Sorry?
Is there like chemical terminology that we need to know?
I'd have to see if I have like a guide handy, but yeah, you want to know like these intermolecular forces. I guess were there certain terms you were wondering about?
Yeah, if we needed to know them.
Oh, like which ones?
Like, if there was a question on the exam, a possible question on the exam that asked us for, you know, certain terms, like a fill in a blank question.
Yeah, I mean, so you want to, I think, distinguish between the intermolecular forces, right? So that's a key point, that we're breaking those intermolecular forces. And I'll see what guides I have, but that's where like the textbook might be helpful since it bolds certain words. All right, so then, right, this is just kind of recapping, well, why are molecules even, right, attracted to one another? So then we can examine water a little more closely. We can draw its Lewis dot structure. And right, it has its two lone pairs. And so these lone pairs are a region of extra electron density. So we can write our partial negative sign. And our hydrogens, right, again, are partial positive, since they're stripped of electron density. And so then we can start to see how these forces, right, line up with one another. And so obviously, right, we have seen opposite charges from either cation to anion, right, complete separation. Or what we're looking at right now is this end of a polar molecule, right? And so what they're trying to emphasize here is, okay, well, we have our water molecule, it's polar. And so then it's going to want a hydrogen bond with another water, right? So then an oxygen from another water molecule is going to be attracted to this hydrogen and kind of hang out over here, like is shown down here as well. So partial negative, right? So again, our negative region is attracted to our positive region. So that's creating, right, our intermolecular force here. And so we'll look at this, how even nonpolar molecules have temporary charges in these little dipoles. So again, we'll look at that, but basically what we're emphasizing, so larger charge gives us a stronger attraction, and then obviously, right, the further they're apart, and the weaker that attraction is. So then we'll start looking at the different types of intermolecular forces. And so we'll start with the weakest one, which is called these dispersion forces, or you might also see several different names for them, so they can also be called London dispersion forces, or also van der Waal forces. So different names, same thing. And so let's look at the picture, because the picture is really more useful. And so we're looking at 3 little helium atoms here. And so basically it's saying, what if we have this instantaneous dipole? And so, right, we can see kind of what's going on. And so let's just say it just so happens that our electrons are on the left side of this helium atom. So, right, this is our partial negative region here, again, because our electrons are here. So if our electrons happen to be on one side, then this creates a temporary partial positive region. And so sometimes, right, this instantaneous dipole can also induce, right, other instantaneous dipoles, so then they're interacting. So now if it's with another, next to another helium molecule, again, where it's on the left side, so now they're temporarily attracted to each other with, again, this positive region and this negative region. And then, right, this is duplicated down on the line. So again, positive region, negative region. But then, right, obviously, this is just a little instantaneous dipole, right? So these electrons aren't just going to hang out on the left side, but they're going to continue, right, rotating round and round. But we do still get, right, that little instantaneous attraction there. So that does have a small effect. So now let's look at that. And so the other thing that we want to emphasize is that all molecules and atoms have these London dispersion forces. It's just a question of, you know, how strong are they, and then obviously, are there other forces? Because like we're saying, these are the weakest, so they have, you know, the weakest effect. And so again, these are caused by fluctuations in our electron distribution as they go round and round. So again, causing a temporary or instantaneous dipole. So again, we saw that here, but then of course it's going to keep moving on and not stay in that fixed region. And so these attractive forces are called dispersion forces, or like I mentioned, London forces, van der Waal forces. And so all molecules and atoms have this dispersion force. And so then we want to predict the effect of the size on these dispersion forces. And so now we're just comparing for physical size. And so as our molar mass increases, our electrons increase, and then our electron cloud is more polarizable. So that means that our strength of our dispersion forces increases. And so this is most reflected in the boiling points of these different noble gases. So again, right, all noble gases, all nonpolar. So, okay, we're just comparing the same type of London dispersion forces. And then, again, helium is the smallest with our molar mass of 4. And then its boiling point is 4 Kelvin, so that's pretty insanely low. And then, of course, as we go up, so neon, argon, krypton, xenon. So now xenon, right, has the highest boiling point of 165 Kelvin, so obviously still pretty low, but just seeing the effect of that larger mass size. And so shape is also really important. And so we want to talk about surface area and how they're interacting. And so now we're comparing pentane versus neopentane. And so the first thing that we want to do is make sure that we eliminate the mass argument. And so, yes, they have the same molar mass. In fact, right, they have the same formula. So they are both C5H12, just different arrangements, right? So pentane is in a line here. So 1, 2, 3, 4, 5. And so it's kind of shown here. So, right, we can already see this area for interaction. We can imagine how they can actually stack, right, almost quite nicely on top of one another. So getting those intermolecular forces, a lot of interaction there. And if we compare that to neopentane, so we have this carbon in the middle here. Sorry, not the greatest tetrahedral drawing. But we can see, right, this is more of a ball shape, and so a lot less area for interaction, right? Just trying to imagine how they would interact. So less surface area between them, right? They're not kind of stacking nicely like those. And so again, we can see that reflected in the boiling point, where pentane has a boiling point of 36 degrees Celsius, whereas neopentane, with much less surface area for interaction, is 9.5 degrees Celsius. That's pretty interesting there. And so then we can also kind of summarize this in our boiling point of alkanes. And so these are all straight chain alkanes, so N-pentane and hexane, heptane, octane, and nonane. And so, of course, we're just appreciating with increasing molar mass, right? We're adding extra carbon on the end at each one of these, and the boiling point, right, increases as well. So just good to appreciate. So that's a mass effect mainly. And then it does want you to note that if you had any branching, then that would have a lower boiling point than a straight chain. Again, thinking about, right, how those straight chains can really stack versus any sort of branching is going to lead, right, to not as good stacking. So that can disrupt, right, those intermolecular forces. All right, then the next force is these dipole-dipole interactions. And so now we have to think back to polar molecules. So this is where it's important to identify what's a polar molecule. And so why we want to identify polar molecules is because they have a permanent dipole. So again, right, that's kind of implied by that polarity, right? We're trying to determine where is that region of electron density. And so again, you've gotten a little taste of this, so we'll keep practicing, right? Again, looking at their polarity. So first looking at the individual bond and then judging its overall shape, which again, you guys have been doing. And then the separation of charges is referred to as the dipole moment. So the dipole moment is something then that can be measured. And so again, we can appreciate our electrostatic potential map. So we're looking at acetone here. So again, acetone has our permanent dipole with our oxygen, so extremely electronegative. And then our carbon, right, we can see has our region of positive partial positive charge. And again, right, with our electrostatic map, so blue kind of indicates a positive region, red is negative. And so then we can appreciate how having a permanent dipole and how something is more polar, this adds to our attractive forces and raises our boiling points. And so let's look at this first argument. So again, we're looking at formaldehyde versus ethane. So the first thing we're going to do is eliminate the mass argument. So different formulas, but their masses are pretty similar. Okay, so we can start there. But then looking at their boiling points, so what accounts for this large difference? So we have -20 versus -88 for ethane. And so if we're looking at ethane, right, it's all CHs, so non-polar, versus formaldehyde, right, well, we can put those lone pairs on those oxygens to help remind us, but we're looking at that, okay, that's our negative region, positive region, so permanent dipole, right, again, we can write there, okay, it's polar, and so just that small difference in polarity accounts for that large difference in boiling points. And so this is just a good guide. So I don't expect anybody to know dipole moments or anything, but what we want to see is, just how to look at it and maybe where to get this information. And so you can also look at Wikipedia. So let's just try one of these out. So let's try propane. See if they're all on there. And so obviously, right, we should guess that propane is pretty nonpolar. Again, it's just CHs. But if you're ever curious, so you should be able to find their dipole moment here. So right, there's the dipole moment. So this is just standard data. And so, right, pretty low, but you want to get context. So, okay, 0.08. So again, I would consider that nonpolar. And then we can look at its boiling point. And so again, the point here is that they're all around 44-ish for their molecular weights. So we don't have a size argument. But then we can at least appreciate, so let's look at dimethyl ether. And again, right, I'm just emphasizing that if you're ever stuck, you don't know whether a compound's polar or not, right, check Wikipedia. That can help guide you a little. So now we're looking at, right, dipole moment, so 1.3. And so that starts to get, right, a little polar there. So we can see these ethers aren't the most extreme. An ether is just an oxygen in the center there. And then again, a little increase in boiling point. And then let's skip over, we'll do acetaldehyde for fun. We're running out of time. And so acetaldehyde, so again, just kind of giving us context. Okay, dipole moment 2.7, so that's starting to get more polar there. So again, increasing boiling points. And then acetonitrile, so that's fairly polar, right, with a dipole moment of almost 4. We can see, right, we have this region here on our nitrogen, a lot of electron density there, so polar, and then a boiling point of the highest at 350 Kelvin. So like I said, at least, right, you can use a Wikipedia to kind of help you. Let's look at it. I just picked one for fun. So acetic acid, see if it has a dipole moment, right? So dipole moment, 1.74. So again, that just helps you kind of put it in context, right? How polar is that? So just to kind of help you judge, since that's difficult. All right, so we're probably going to stop there in the interest of time. But you can see where we're going. So we'll pick back off with hydrogen. So even a more specific dipole-dipole interaction. But again, we're seeing how more polar things are more attractive in those forces. All right, I will see you Wednesday.